Hey guys, this video is on chapter 21, second last chapter of your syllabus, Electromagnetism. But before we begin our study of electromagnetism, it is important for us to recall some factors or some facts that we learned from the previous chapter, Magnetism. Alright, so these are relevant facts and details are directly related to your study of electromagnetism. So it is important for you to recall or at least have them at the forefront of your thought as we study electromagnetism. First and foremost, properties of magnets. Magnets have two poles, north and south. Magnetic effect is strongest at the poles. When you freely suspend a magnet, it will always come to rest in the north-south direction. The north of the magnet will point to the geographical north of Earth. Some other properties that are important: like poles repel, north and north, south and south. When you bring them together, they will repel. And unlike poles, north and south, when you bring them together, they will actually attract. Some other relevant points: magnets can be broken up into smaller and smaller little domains called magnetic domains. Now, when these magnetic domains are all pointing in random directions, we have an unmagnetized bar, or rather the bar shows no magnetic properties. When I do certain things and I cause the magnetic domains to all align in one direction, then the bar will express some magnetic properties. Now, it is also important for us to remember how we can change from this configuration to this configuration and how I can change it back. Alright, in our magnetism studies, we actually learn of a few methods to actually form a magnet. That means from a random magnetic domain, all of the domains pointing in all different directions into all of them pointing into one direction. Alright, the first that we learn is we can stroke it with a magnet. You stroke it enough times, then all the domains will point in one direction. Another method, you can use the electrical method using direct current. Alright, if you recall from your study current of electricity, direct current only flows in one direction. It is the direction of conventional current, which is from positive to negative. And when I run and when I put a rod in the center of a coil, it will cause all the magnetic domains to align in one direction. Now, it is important for us to understand or to know which poles are being induced when I run the current in a coil like such. Alright, if you recall, we use something called the right hand grip rule. That means it's just your right hand in a thumbs up sign. Sorry, let me zoom out a little bit. Alright, your hand in a thumbs up sign as such. Alright, your fingers will actually follow the direction of the current in the coil. So in this case, it will actually go from the back of the coil to the front. So your thumb actually points to the right. So therefore, the right side of the coil is actually north. Alright? To demagnetize a magnet, meaning I change the direction of the magnetic domains when they are all aligned to something that is randomly aligned, I can use a few methods. One, I can hit it with a hammer. This will cause all the domains to be disaligned. Heating also will have the same effect. Another way, more importantly, is the use of AC current. Now, AC current is one where the current actually changes direction many times in 1 second. So this will cause all the domains to align here, and then align the other direction, align here, align the other direction, and then as you slowly withdraw the magnet, you will have a bar with totally random magnetic domains pointing in all different directions. Now, the final thing we need to recall about magnetic field patterns. Alright, the magnetic field patterns of a bar magnet always originate from the north and they always end up pointing to the south. So this is important. Magnetic fields point from north to south. Alright, now we are ready to begin officially our study of electromagnetism. Three things we'll cover in the chapter: magnetic effect of current, motor effect, and turning effect of a current carrying coil in the magnetic field. Now, the first two will be what is covered in this video. The last one will be covered in class. Alright, as we recall just now, when current flows through a conductor or coil of wire, actually you produce a magnetic field, and that's why I can cause the magnetic domains to all align in one direction. Alright, this phenomenon is called making an electromagnet, in which I use electricity to induce a magnetic field to appear. Now, this was first discovered by Ørsted. He was a scientist. He first discovered it when he was actually giving a lecture in class. He was doing some lecture on magnetism, and he realized that whenever he had current flowing nearby, he would actually cause the magnets to disalign from its original north point. I mean, the magnets are always pointing to the north. When there has current flowing through somewhere nearby, it causes the compasses to actually deflect. So he did a little bit more study. He realized that when he actually placed the magnet one below and one above, and the current flows through the wire, he realized that actually the one above will always point to the right, and the one below will always point to the left. So he realized then that actually current, as it flows, produces a magnetic field, and this is the most important thing about this chapter. Through his study, Ørsted discovered that when current flows through a straight wire, the magnetic field produced actually consists of circles, in fact concentric circles. And he also noted that the magnetic field is stronger closer to the wire. Therefore, when we illustrate our magnetic field lines of a straight wire, you show that the magnetic field the magnetic field strength is stronger nearer to the wire by drawing the field lines closer when they are nearer to the wire. Recall our study just now. We use our right hand grip rule to discuss and identify the direction of the north pole by our thumb by curling our fingers in the direction of the current in the coil. Now, we do not have a coil here, but rather we have a straight wire, but the right hand grip rule actually still applies. In this case, the thumb points in the direction of the conventional current flow, and where the finger curls is the direction of the magnetic field. So the magnetic field actually curls in this direction if my current flows in this direction. Alright, so just take note, direction of fingers is the direction of the magnetic field. Alright, we did a little bit of study here, but I'll just help you guys remember. When I have a circle with a dot in the center, it represents current flowing out of the plane of the paper. When I have a circle with an X in the center, it actually represents the current flowing into the plane of the paper. That means flowing into this direction. Over here is coming out of the plane of the paper. So he noted that when the current flows in this up direction, here, the magnetic field actually curls in this direction, and when it's going into the plane of the paper, actually the magnetic field curls in this direction. So when I change the direction of the current carrying wire, then the magnetic field direction is also reversed. What is also noted is that if I increase the current flowing through the wire, current 1 here is less than the current in here 2. He noted that the magnetic field strength shown is stronger here. So the greater the current, the greater the strength of the magnetic field. Now, we did our study of the current flowing in a straight wire. So what if the current actually flows in a coil? If the current flows in a coil, we can actually use the same concept as the straight wire. So if the current flows from here to here, then over at this point, actually it is coming out of the plane of the paper. So we can draw the magnetic field lines as such in the clockwise direction. Sorry, in the anti-clockwise direction. Over here, if it's going into the paper, then it's actually in a clockwise direction. So from here, he managed to generate this magnetic field. He also noted a few things. He can increase the current to increase the strength of the magnetic field around the wire. He realized also he can increase the number of turns of coil to increase the magnetic field strength of the coil. Now, because of this and the right hand grip rule, we realized that when I have a coil of wire as such, that the magnetic field lines that are formed look very similar to a simple bar magnet. So this is where our right hand grip rule comes into play and how we determine that the direction of the thumb is the direction of north. Because when you draw out the diagram, it actually comes out from this direction and goes into this direction. You recall the magnetic field lines always move from north to south, north to south. So he realized that he can use the right hand grip rule as a tool to identify the direction of the north. Alright, just a little bit more explanation on this slide. The direction of the fingers indicate the direction of the current. The thumb indicates the direction of where the north would be, induced. Now, other than increasing the current and increasing the number of turns to increase the magnetic field strength, he realized also that you can place a soft iron core within the coil of wire, and this will actually also increase the magnetic field strength. Now, there are some direct applications of electromagnets. One of them is circuit breakers. So what are circuit breakers? Circuit breakers are safety devices that switch off when you have an excessive amount of current flowing through. Alright, so one of the biggest and most important component of the circuit breaker is actually an electromagnet. So we'll explore how it works. Alright, this is a diagram of an electromagnet, of a circuit breaker, a simple one. Alright, you have the live wire here. It flows through here and is wound around a soft iron core. It exits out here through the contact and out here through the interrupt point. Now, if the current is flowing in a safe limit, then this fella here does not become a strong electromagnet. If you recall, we just studied, the greater the current, the greater the strength of the electromagnet. So, since the electromagnet is not strong enough, it is unable to attract the safety bar, unable to attract this soft iron latch here. So the bar stays in place and the interrupt point and is working in normal operating conditions. Now, what happens when I have an excessive amount of current flowing through? When I have an excessive amount of current flowing through, then this wire here, or the coil here, has an excessive amount of current flowing through. The greater the current, the greater the strength of the electromagnet. Now it is strong enough to attract this soft iron latch. Now, this soft iron latch was actually holding this safety bar in. The safety bar is spring-loaded. So once it's attracted, there's nothing holding back the safety bar. The spring will release and it will push the safety bar out. At the same time, this will break the contact at the interrupt point. So now you have an open circuit. So the end effect is that when I have too much current flowing through, then my my circuit breaker will actually break open the circuit and no current can flow through. This will prevent any damage to your equipment, prevent any fires from happening. So this is one of the safety devices, and this is how it works. Alright, of course, very simply, if you have already fixed whatever was causing the problem, either a faulty appliance, then all you need to do is actually to push the switch back in. Most houses is actually switch the back up, and then actually it will go back here. The latch will hold the safety bar back in place, and if everything is working fine and current flowing through is small, then this will no longer be strong enough to attract the safety latch. Alright, going on into the second part of the chapter, the Moto effect, forces due to magnetic fields. Now imagine I have a setup as such. A circuit here with current flowing through this wire here. When I close it, the current flows in this direction from A, B, C, and to D, and then back to the dry cell. Now, when current flows in A, B, C, D, you have a magnetic field being set up by this current. So now what happens when I have this current carrying conductor with current flowing through, which then has its own magnetic field in the presence of a permanent magnet? Then actually basically what you have is a magnet because of the current, and a magnet here. You will either have a repulsion or an attraction. So the current carrying conductor will have a magnetic effect. The magnet has its own magnetic effect. So when the magnet, due to the wire, and the permanent magnet meet each other, then you either have a repulsion or attraction, and therefore a force will cause this wire here to swing out. Now, if I were to switch the direction of the cell, and the current now flows from D, C, B, and then to A, then he realized that actually the wire swings inwards. Now, you know this, you can understand this because when the current flows in the opposite direction, the magnetic field also flows in the opposite direction. You recall from our study right-hand grip rule, alright, if I change the direction in the opposite direction, then the magnetic field actually flows in a different direction. Get it to focus. Alright, so not only can you switch the direction of the current flowing, you can also switch the polarity of the magnet, meaning you make the north here and the south here, and then you will also have the same effect. The wire will actually move inwards in the opposite direction. Now, it seems all very complicated because it is simple enough when you have It's simple enough when you have a coil of wire and it's easy to identify where the north is. But when you have a straight wire as such and the magnetic field actually moves in this direction, then it becomes very hard actually for you to identify where is the north and where is the south. So it is a challenge for you to identify where actually the force is acting on the wire. So Fleming, he devised an ingenious method for us to identify the direction of the force that is being felt on a current carrying conductor as when it is in the presence of a magnetic field. Alright, so I'll explain this a little bit first before I zoom out and show you how it looks like. Fleming's left-hand rule states for you to deduce the direction of the force on a current carrying conductor in a magnetic field, you can place your hands in this manner. Alright, like how you make a gun and then you stick out your middle finger, all 90 degrees to one another. Alright, the thumb points in the direction of the force, your index points in the direction of the magnetic field, your middle finger points in the direction of the conventional current. Alright, so when you align your magnetic field and the current in the correct direction, you can identify the direction of the force being felt. Alright, so You can recall or you can remember this by a simple method: father, mother, and child. From thumb to index to middle finger. The F represents the force. The M in mother represents magnetic field. The C in child represents the current. Thumb, index, and middle finger. Just be a little bit careful. When we're talking about the magnetic field, you must recall that it points from the north to the south. North to south. And for the current, we are actually talking about conventional current. Alright, so let's just put what we learned into practice. What happens when the switch is closed? Conventional current flows from positive to negative, so it will flow here. So it will flow in this direction, out the switch, and back to the negative. Magnetic field always points from north to south. So how you would go about doing this? First, align the magnetic field. Recall, magnetic field points from north to south, so point in the direction of the magnetic field. Current, just point in the direction of conventional current, and therefore you find that the force is actually acting upwards on the current carrying conductor. So what will happen to the wire is that it will actually move up. Now, what will happen if the magnetic poles were switched? Now, instead of having north here and south here, you switch such that north is here and south is here. Alright, a little bit of twisting. You will see these people doing this in the exam. North to south, magnetic field point in that direction, the current points in this direction, the force acting downwards. So actually, the force felt on the wire will actually cause it to move downwards. Alright, so it moves up in the first situation, move down in the second. Now, officially, how do I explain this? Alright, the force being felt on a current carrying conductor. Now, whenever they ask you why is there an induced force, why is there a force being felt when current flows in a wire in a magnetic field, the official explanation is this. And you better write this down in your notes because it's not in your notes. Magnetic field due to the current interacts with the magnetic field of a magnet. So the magnetic field of the current and the magnetic field of the magnet, these two will interact. You have a resultant magnetic field, and this is what exerts the force on the current carrying conductor. Now, how does this look like? Alright, if you have a current in a straight wire pointing into the paper, and it exists in the field of a permanent magnet, north and south, how this will actually look like, draw them together. Let me zoom this in. So you realize that over to the left side of the wire, the field lines on the left side of the wire are pointing in the same direction as the field lines of the magnet, north to south. They are both pointing upwards in this case. So they amplify the effect. So what you have is a strong magnetic field pointing upwards in this direction. Now, over on the right side of the wire, the magnetic field lines due to the current actually are pointing downwards, which is directly opposite to the north and south of the permanent magnet. So actually they cancel out each other. So you have a very weak magnetic field here. Now, as an end result, what you have is a very strong magnetic field on the left side of the wire here, due to them being amplified, and a very weak because they cancel out each other. Now, the stronger magnetic field will actually push on the weaker magnetic field, and this will cause the wire to move in this certain direction. So this is officially the explanation that you have to give in an O-level exams whenever they ask you why there's an induced force. Now, what happens when I have two parallel current carrying conductors? Means you have two wires and they are both pointing in the opposite direction, or rather the current is pointing in the opposite direction. One coming out of the paper, one going into the paper. Now, if you bring them close to one another, you realize that these two fellas here will meet first. These two fellas are pointing in the same direction, which is upwards, and they will amplify. So the magnetic field between the wires will actually be stronger. Over here, there's no effect. So you have a stronger magnetic field in between the two wires and a weaker field on the outside. This will actually cause them to move away from one another. Stronger push on the weak. So actually, the end effect is that these two wires will move away from one another. So what we say is that they have a repulsive force. What happens if I have two wires next to each other and they are both pointing in the same direction? So when you move them closer to one another, you realize that this fella is pointing upwards and this fella is pointing downwards. As a result, these two fellas will cancel out each other and over here remain the same. An effect is that you have a very weak field in between the two wires and you have a stronger field on the outside. So actually the strong field will push on the weak field and the two straight wires will actually move towards one another. So an effect, move towards one another, so attractive force. Now this is another common question type. Again, you use your Fleming's left hand rule to solve this type of question. What happens if I fire a positively charged particle into a magnetic field? Now, oftentimes in O-level, they will actually show your magnetic field in this direction. This means that a magnetic field, when you have an X, just similar to how you have a current carrying conductor, how it's symbolized, like this, it shows that the magnetic field is pointing into the paper. That means, if you can imagine it, you have a north on top of the paper and a south underneath the paper, magnetic fields pointing into the paper. Alright, if I have a positively charged particle and I fire it into this magnetic field, what will happen? Now, if you recall, this positively charged particle is the same direction as conventional current. Just a little bit of reminder, conventional current flows from positive to negative. It is the direction a positive charge would move, if it could move, because it's repelled from the positive and attracted to the negative. Now, as a result, it is the direction opposite to that is actually the direction of the electron flow or the negative charge. So recall that when you talk about Fleming's left-hand rule, you have father, mother, and child. This C, your middle finger, actually points in the direction of the conventional current. So conventional current, direction of positive charge. So let's do this. Fleming's left-hand rule. Father, mother, and child. Magnetic field pointing into the paper. Current pointing towards the left, because the positive charge is moving to the left, is the direction of conventional current. As an end effect, the force being felt is upwards. So that's why, as you see from the diagram, when you fire it into the magnetic field, the positive charge will eventually move upwards. What happens if we have a negatively charged particle? Recall, negatively charged particles move in the direction opposite to positive, which is the direction of the conventional current. So negatively charged particles move opposite to conventional current. So again, we illustrate this. I'll show it to you. Magnetic field into the paper. The current by right is supposed to be like this, but it's an electron flow, so it's actually opposite to that. So the direction of the force felt is actually downwards towards the paper. That's why if you see the path of the negative charge, it will actually move downwards. Now, you can also illustrate the magnetic fields coming out of the paper with a circle like this. Also is quite also commonly shown as such. So if you see something like this, it means the magnetic field is coming out of the paper. So if I fire a positively charged particle towards a magnetic field, it's coming out of the paper. Again, use Fleming's left-hand rule. Coming out of the paper, the magnetic field, the current is in this direction. The force being felt is actually downwards. So actually, you see the positively charged particle will move downwards. Alright, so this covers the first two portions of the chapter. As holiday homework, turn to page 206 of your workbook. Look at the table found at the back. Do all questions related to the learning objectives A to F. Your teachers will go through the answers when we come back. Alright, thank you. That's all for this video.